Hey everyone, today we're going to talk about banked tracks. This is relevant if you've ever seen NASCAR or if you've ever even taken a very sharp turn. You may notice that the road is a little bit banked, which means it just comes at an angle to help you stay on the road a little bit. This is a very small part of the AP curriculum, but it's definitely good to know. So first let's look what happens when a car rounds a curve on a flat road. We know that the net force acting on it is the centripetal force that's pulling it in towards the center. Which force is responsible for that centripetal force? Usually it's the force of friction. So we'll say between your tires and the road, the force of static friction is equal to mv squared over r, since the friction is our net force and that is responsible for the centripetal force. So as V starts to increase, as you start to go faster and faster, what you all should start to realize is that it's harder to maintain your car on the road. You know that you have speed limits around curves for a reason, because if you go too fast, your car can tip over. And the reason your car can tip over is because you exceed your maximum friction force. So what we would need to do is basically plug in our mu and Fn to figure out how fast we can actually go. So I'm going to go ahead and quickly solve for that in terms of, variables. So we know that our Fs is going to be equal to mu Fn equals mv squared over r. And I know your guys' favorite part is when we start to cancel things out. So let's make this mu mg equals mv squared over r. Now our masses can cancel yet again, showing you that it doesn't really matter how heavy you are. And you'll see mu g equals v squared over r. This should not come as a surprise because we've already done the calculations to cancel things out to show that mu g equals a. And since our centripetal acceleration is v squared over r, this is the same equation. So again, what velocity would we need to travel with? Well, we get v equals mu g r under a radical. And there's the velocity that you can travel with safely on a curved road. I guess you would have to say that the velocity would have to be less than what this value gives you. Now, in order to reduce the chances of skidding, you may not notice it, but a lot of roads are banked, which means they're just tilted a little bit. They're on an angle. So for instance, if we're looking at it from a cross-sectional area, where a flat road would look something like this, a banked road would look like this. Okay, and it might have, 8 degrees, something small. So what happens with this, the reason why they do this is because then it allows us, our normal force, to have some component that reaches out here that helps to contribute to the centripetal force. If a component of our normal force is pointing towards the center, it allows the friction force to not totally be responsible for the centripetal force. Since the centripetal force is pointing in, we have the component of friction and the normal force to kind of help reduce the skidding. Once you reach a certain speed, though, all of the centripetal force will be the responsibility of the normal force. So let's kind of get into that. So here's a pretty extreme angle, but I want you guys to be able to see what I'm doing. So here we have mg. You have your normal force. And what you'll have is the component of the normal force in the y. And you'll have your component of the normal force in the x. So what this means, and if you'd like me to do the trig out for you, I can in class, that nx is equal to n sine theta, and ny is equal to n cosine theta. And now let's say with no dependence on friction, so the normal force is the responsible force for the centripetal force. Let's set up our F net equals ma equations for our x and for our y. So the same thing as before, our net force in the x is going to be our nx, and that's responsible for the centripetal acceleration. So we're going to have nx equals mv squared over r, which means n sine theta equals mv squared over r. Over in our y, we have the y direction of the normal force, and we have our weight. But notice that the car is not traveling, or is not accelerating up or down. So we'll have, we're calling this n. We'll have ny minus mg equals 0. So n cosine theta equals mg. And now what we can do is we can solve for the normal force, we can solve for theta. What we can do from here is we can solve for the velocity that we can move at. We can solve for the angle that it needs to be at. We can go from a bunch of different things. So let's first look at the angle. So now let's solve for n, and we can plug that into our other equation to solve for velocity. We'll take this and we'll plug it in here, and we will get mg cosine theta times sine theta equals mv squared over r. And sine over cosine, we know, is tan theta. So we get mg tan theta equals mv squared over r. Our m's cancel yet again, and we get tan theta equals v squared over gr. So our banking angle here is the inverse tan of v squared over gr. Now, if we tried to use this to solve for velocity, we can do this kind of the same way. So let's go back. Our m's still cancel, and instead now we're going to solve for velocity. So we get rg tan theta equals v squared. We can get rid of the squared by putting both under the radical. And we're left with the velocity on that track that's safe enough is dependent on r, the radius of it, g, and theta. And I know that's a lot and it's a little confusing, but please raise your hand during class. We'll talk about this when I go over this video, and I think you guys will be okay.